Okay, here we are for the last videos of today's lecture, and so the first thing I want to stress in this video is a statement that I gave you as a granted in previous video, but it is not like that, it is not so simple. So in the previous video we used the fact if f is continuous at the point x bar, and xn is a sequence in the domain of f, with xn converging to x bar, then f of xn tends to f of x bar, namely, this is the version in which we used this statement, the limit of f of xn is equal to f of the limit of xn. And so we can give the following sentence that says for a continuous function it is possible to take the limit outside the argument. Good. This is this is the message. This is the important message one has to convey. And since this rule will be used several times, and also you in the exercise will have to use it, one has to understand it very well. And so we give a proof of that. First point, if xn is an isolated, if x bar is an isolated point, so it is not an accumulation point, then the fact that xn in the domain converges to x bar implies that xn is eventually constant, so is eventually equal to x bar. Otherwise, there is no way to approach arbitrarily close a point, an isolated point. Then f of xn is equal to f of x bar eventually, which implies that f of xn converges to f of x bar. Okay, this is the first point. Second, if x bar is an accumulation point, then you have that f of xn will converge to limit for x to x bar of f of x by LTS. First step. Okay, we are considering a sequence converging to x bar, xn converges to x bar, so provided that this limit exists, but it exists because f is continuous, provided that this limit exists, f of xn will converge to this limit. But of course, this is f of x bar, since f is continuous. Which is, of course, lim f of the limit of xn. So this is the explanation on the basis of the theory of of this simple rule that holds for f continuous. And I stress it by writing here again, so be careful. In order to write this simple rule, f must be continuous at the point x bar. Very, very important. Okay, so now I give you some corollary of the theorem of existence of zeros. The first corollary, remember corollary is an easy consequence of the theorem. So the first corollary I give you is the following. You have a function f defined this time on an open interval. The interval can be unbounded, which means that a and b belong to R bar. And you have that the limit for x going to a from the right of f of x is negative, and the limit for x going to b from the left of f of x is positive. And of course, f is continuous. This is the picture we can refer to. For instance, here there is an asymptote here in A, and here there is B. So this is A, and this is B. And of course, in this case too, there must be at least one point where f vanishes. Okay, then there exists a point L in AB such that f of L is equal to 0. Okay? And the proof is very simple. The proof relies on the fact that we only know the limits, but since the limit in A is negative, by permanence of sign, there must be some A prime here where the function is negative, and some B prime here where the function is positive, and then we apply the theorem on existence of zeros on the restricted interval A prime, B prime. So, give you the proof. And we have that by permanence of sign, there exists a U in a right neighborhood of A and V in a left neighborhood of B, such that for every x we have that f of x is less than 0, and for every y in V we have that f of y is positive. Then consider 2 points A prime in U and B prime in V, and apply the theorem of existence of zeros to the interval A prime, B prime, which is in this case closed and bounded. Then there exists L in A prime, B prime, which is contained in AB, such that f of L is equal to 0. Okay, this is a very simple extension. And okay, as a remark, we have that A, B, the limit for x going to A from the right of f of x, and the limit for x towards B from the left of f of x may be infinite, plus or minus infinite. And another corollary, the second corollary, it is very important, so it has the name of a theorem too. And the complete name is the intermediate value theorem. It says the following, that if you have f from AB to R, then f takes all values in the interval inf f in AB and sup f in AB. Or equivalently, f of an interval AB is equal to the interval between the infimum and the supremum. Okay, this is the first easiest version, but one can easily prove that the theorem holds also if the domain is an open interval and or unbounded. So the message of this theorem is the following. The image of a continuous function, the image of an interval through a continuous function is an interval. Or, again equivalently, a continuous function maps intervals into intervals. This is extremely important, and again, a picture can clarify many points. Here you draw the graph of a continuous function here, and then you see that the image lies between the infimum, which here is a minimum, and the supremum, which in this case is plus infinity, since here I wanted to mean to be an asymptote, a vertical asymptote here. And so this is the image of f, the range of f, okay? And of course, again, here we can give a proof, and the proof is the following. Consider a point C in the interval between the infimum of f and the supremum of f, we want to show that there is an L in the interval AB in which f equals exactly L. So define a function g of x is equal of f of x minus c. Of course, g is continuous in AB. Now, the first thing to notice is then there exists an x1, a point x1 in AB, such that f of x1 is less than c. Since c is larger than the supremum. Since c is larger than the supremum, and remember that, is larger than the infimum. Remember that the infimum is the largest between the lower bound. If it is not true, c will be a lower bound. Okay, this is the typical reasoning with infimum and supremum. So analogously, there exists a point x2 in AB such that f of x2 larger than c. Since c is less than the supremum of f. Okay? Then, now, we have that g of x1, which is f of x1 minus c, must be less than 0, because f of x1 is less than c. And g of x2, which is equal to f of x2 minus c, is larger than 0. Because of this, f of x2 larger than c. Therefore, applying the theorem of existence of zeros to the function g in the interval x1, x2, if x1 less than x2, we don't know, or x2, x1. In the opposite case, so if x2 is less than x1, then there exists in x bar, in which interval, let me write this in a shorter and more clever way, in the interval x1, x2, union x2, x1. This is a strange way to write things, and perhaps students always get confused by that, but indeed it is very simple. This is empty if x1 is larger than x2. So if x1 is larger than x2, the only interval that remains here is x2, x1. On the other hand, this is empty if x1 is smaller than x2. So this is an easy way to write interval x1, x2 if x1 less than x2, or x2, x1 if x2 is less than x1. Okay? So don't get scared of that. It's just an easy way to write it. We will use it a lot in the theory of derivatives, especially in the differential calculus. Okay, so there exists an x bar there such that g of x bar is equal to 0, but remember that g of x bar is equal to f of x bar minus c, So this means that f of x bar is equal to c. And this is the end of this proof. Remember this stuff here, because of it will appear in many exercises, and I want just to stress you what we did with notation. Notation says that AB union BA with closed interval is equal to AB if A less than B, BA if B less than A, and A if B equal to A. Okay. Now let us go to the last part, which is on theorem of existence of maximum. This is Weierstrass theorem. So first of all, we give a definition, maximum of a function. As usual, we have a domain E in R and a function f from E to R. We define the maximum of f in the domain E. This max f for x in E is equal to the maximum of f of x with x in E. Very simple. And the minimum of the function f in E, the minimum of f of x for x in the domain. And now let me stress the following remark. In general, max f and min f may not exist. Let me give you a very easy example of this possibility. Consider the function f from R to R that associates to every x the function 1 divided by 1 plus x bar. This is the so-called Lorentzian function. And okay, and notice that here we have a maximum of f which is equal to 1, but the minimum does not exist. There is an infimum of f which is 0. The point is, as usual, very simply, that 0 is not reached. It's just a limit when f goes to plus infinity. And of course, notice that here the range of f is an interval, but it is a semi-closed interval. It's 0 open, 1 closed. Okay, we will reason a bit on that. So in general, may not exist, but it is the content of Weierstrass theorem, but if f is continuous on a closed and bounded interval, then maximum and minimum exist. Okay, so Biostar's theorem states exactly the following thing. So I write here theorem officially due to Biostar's this says let A be smaller than B, A and B real numbers, of course, F defined on the closed and bounded interval AB. This is very important, closed and bounded. Okay, F continuous implies that there exists the maximum of F on AB. This means again, namely, there exists an X bar in the closed interval AB such that f of x bar equals the maximum of f of x when x belongs to the interval AB. Okay, now, so attention, because this is a nice, very nice proof. Okay? So, the first remark is very simple. We say that the set, the range of f, which is the set of f of x for every x in AB, so with another notation that I want you to know and to use possibly, f of the interval AB is not empty, is a non-empty subset of R, so it has a supremum that we call psi. Okay? So we want to stress the fact that the supremum will be finite and will be reached by the function. This is our purpose. Okay? Then there exists a sequence yn which is contained in this range f of AB such that yn goes to psi. Notice that psi may be plus infinity up to now. Okay? Let us prove this fact. Indeed, if f of AB is bounded, then psi is real number, very simple, and for every n there exists a yn in the image f of AB such that yn is larger than psi minus 1 over n. Okay, this is the usual trick to construct sequences that go to the supremum when the supremum is finite. So we have that yn is not larger than the supremum, strictly larger than the supremum, minus 1 over n. And so by double comparison theorem, this goes to xi, this is constant to xi, and this implies that yn tend to xi by double comparison of two carabinieri or policemen. So when xi is finite, which means the range is bounded, we have a sequence that goes to xi. But on the other hand, so f on the contrary, f of AB is unbounded. Oops, sorry. F of AB unbounded. For every n, there exists a yn in the image such that f of yn is larger than n. Then, by simple comparison, n goes to plus infinity, then f of yn goes to plus infinity, which is the supremum. Because f of AB is unbounded. So in both cases, we have that. So in every case, there exists a yn in f of AB such that yn goes to psi. Okay? Now, since yn is in the range, it must be the image of some xn, which means that there exists an xn in AB such that f of xn is equal to yn. And of course, xn is bounded. Why? Because xn always lies between a and b. And now you know what happens. It means by Bolzano-Weierstrass for sequences, it means that there exists a subsequence x and k, subsequence of xn that converges. So we have x and k tends to x bar again in AB. Okay, it must lie in the interval because of permanence of sign, basically. Now, since f is continuous, and now we exploit continuity, because up to now continuity was just there. But since f is continuous in AB, we have that the limit for k going to plus infinity of f of x and k is equal, for the lemma we proved at the beginning of the lecture, the limit for k going to plus infinity of x and k, which is f of x bar. But the limit of f xn k is the limit for k going to plus infinity of y and k. Y and k is a subsequence of yn, so this limit is equal to psi. So what we prove at the end is that there is an equality between psi and f of x bar. Then, as a consequence, first, psi is finite, since f of x bar is finite, because this is the image of x bar. Moreover, psi, which is equal to the sup of FAB, belongs to FAB. Why? Because it is f of x bar. So it belongs to FAB. So psi belongs to the set of which it is the supremum. So therefore, psi is not only the supremum, psi is the maximum of FAB. And this is the end. This is extremely nice. In my opinion, this is really nice. And now, so the very theoretical part is finished, but there are some comments and applications. First of all, how this proof works. So now the idea of proof, I give you the idea of proof after the proof this time, but I find it very instructive again. The idea of proof is the following. So first, you look at the supremum, but let me do it with the minimum, not with the maximum, for the minimum. First you start that there is an infimum. There must be an infimum. The infimum is here. The infimum of f. Then you say, since there is an infimum, remember in the proof I just gave is the supremum, but it is completely analogous for the infimum, there is a sequence on the image, yn, that goes to the infimum. The sequence can be translated backwards on a sequence of points in the domain. Notice that here, in this picture, for every point of yn, we have two possible choices of xn. But notice that here, what says the theorem is that for every yn there exists at least one xn. Choose the xn you prefer. There are two. This is the first, this is the second. You can choose whatever you want. At the end, what you find is a sequence in the domain, in the interval. For instance, this sequence here of the point that I'm drawing here. So notice that this sequence converges to somewhere. The sequence converges to somewhere. Of course, you can extract a subsequence, for instance, a monotonically increasing subsequence in this case. But at the end, you go to the minimum point. Just a remark which is a bit more refined, so if you don't catch it, don't worry. In the case of the picture, you don't need to extract subsequences from the sequence in the domain, because it is convergent to here, even if you don't extract. The problem of extracting becomes necessary when you have two minimum points, okay? When you have two minimum points to the same minima, for instance, if you had here another bump like this. If you have this, then you could have sequences of xn converging here and other converging here. Then you have to choose by instructing a subsequence. This is the only point. Okay, but the idea of the proof is this one, and of course, in my opinion, it's beautiful. It's an example of beauty of mathematics. And now, let me give you some examples that show you that all hypotheses are important here. So the example says, first, f from AB to R, continuous. I opened the interval here in A. There is not always, so max, min may not exist. So if you consider f from 0 open, 1 closed to R, that associates to every x itself. So you have that f of 0, 1 open at 0 is 0, 1 open at 0. So you don't have minimum. There is an infimum, but not a minimum. There does not exist the minimum of f. You can easily realize this fact by considering here the graph, and the graph is very simple, and here 0, 0 is not in the graph, so the minimum is excluded. Second, you have f from 0 plus infinity up to R. Again, the same function, x, f of 0 plus infinity, so the image is 0 plus infinity, so there is no maximum. And the third case, f from AB to R and f not continuous in all point of AB. Also in this case we can provide some counterexample, for instance, f from -1, 1 to R, associating to every x the absolute value of x for x different from 0, and 1 for x equal to 0. And here the graph is the following. Sorry, not here, but here on the top. This is the level 1. And here again, you have that f, the image f of -1, 1 is equal to 0 open, because 0 is not in the image, 1. So there is no minimum. So all hypotheses, boundedness of the interval, closeness of the interval, and continuity of the function, all the hypotheses are necessary. And now let me give you a very interesting corollary. To Biostar's theorem, which is an example of a fixed point theorem. Fixed point theorem is very important in analysis. You have f from AB to R with the range of f included in the domain. This is extremely important, included in AB. Then there exists an x bar in AB such that f of x bar is equal to x bar. Proof. Very easy. Consider g of x is equal of f of x minus x. Oh, sorry, not to Weierstrass, but okay, it's again Weierstrass, but to existence of zeros. G of x, f of x minus x. This is continuous on AB. So we have g of a is f of a minus a. Since f of a belongs to AB, this is larger or equal to 0, and g of b is equal to f of b minus b, less or equal than 0. Notice that here we don't have strict inequality, but we have also equal, so we have to discuss all cases. So the first is that f g of a is equal to 0, then f of a is equal to a. And then the fixed point is x bar equal to a. Analogously, if g of b is equal to 0, then f of b is equal to b, then x bar is equal to b. If g of x less than 0, sorry, g of a is less than 0, and g of b is larger than 0, then there exists an x bar in AB by existence of zeros such that g of x bar is equal to 0, which means f of x bar is equal to x bar. And if g of a larger than 0 and g of b less than 0 is like in the previous case. This is the end of the proof, but the picture here is very explanatory because here you have AB, the domain, and here you have the same AB as image. So the graph of the function is here. The function is continuous, so the graph can be displayed by a continuous line without keeping the pencil far from the sheet. But this will always have some intersection with this line y equal to x. And so here, these 2 points are 2 possible x bar. This is very easy. And the very, very, very last thing to be said is another corollary or application of the intermediate value theorem. is the following. Consider the Earth. Why not? And now in this time of global warming, this is horrible. I want to draw. Here we have the North Pole. Up. Here we have the North Pole. Here we have the South Pole. And of course, first, by Biostar, we know that there is a maximum of temperature. I don't know, perhaps, I don't know, in Sicily, Tunisia, Sahara Desert, and so on. And second, there exists also a minimum. For instance, here. Suppose that we are in summer, minimum of temperature. Now, intermediate value tells you that there exist two places fix a temperature T between the minimum and the maximum. There are at least two places, here and here, where the temperature is T. Of course, here we have frozen the time, but this is an example on how a very general theory in mathematics gives you a straightforward conclusion on, I don't know, the natural phenomena. The underlying hypothesis the temperature is a continuous function. And of course, you can repeat this reasoning for every meridian. Okay, I was too long perhaps today, but in my opinion, it deserved to be too long. Okay, have a nice work and see you.